University, as well as the Middle Tennessee State University. He got the MS in mathematics from Marquette University and his PhD in mathematics from the Pennsylvania State University. The area of his research is mathematical logic. He is interested especially in non-classical logic, namely intuitionistic and paraconsistent logic, with computability theory via a model for higher order intuitionistic logic based on the Turing degrees. So I request Professor Basu to please present his talk.
Thank you, Monidipadi, for this very generous introduction. So today I will talk, let me share my slides first. Are my slides visible?
Yes.
Okay.
Yes.
So this is the topic of my talk today, left variable inclusion and restricted rules companions of logics. This is a joint work with Professor Mihir Chakraborty. It has recently been published in the Logic Journal of IGPL. So this is the scheme of the talk. I'll quickly go over some preliminaries before I go into the actual topic. There is nothing new over here. It's just some state settings, so some notations, some terminology that I'm going to be using throughout the talk. First of all, a logical language is just a set of connectives or operators. Each operator will have a fixed arity. Then we have a set of propositional variables, which we will denote by V. Given an L and a V, the formulas are defined as usual inductively. And then by boldface FM, we will denote the formula algebra. This is the algebra of terms or formulas. This is actually an absolutely free algebra of type L over the set of generators V. The universe of this formula algebra will be denoted by the regular face FM. Now, in order to define a logic, we also need a consequence relation. So a consequence relation is understood as a relation from the power set of the universe of the formula algebra, that is P of Fm to Fm. We automatically assume, so when we talk about consequence relations, we will mean Tarskian consequence relations, which means it will satisfy the conditions of reflexivity, transitivity, monotonicity. These are as usual. Then in most cases, in fact, in all of the cases that we will discuss, we will talk we'll work with substitution invariance. So a substitution, first of all, is a function from the set of generators V into the universe of the formula algebra. This extends uniquely to an endomorphism of the formula algebra FM, again because of the universality property or universal mapping property. Now, a consequence relation is called substitution invariant if it satisfies this rule of structurality, that is, if you have sigma, a set of formulas, and a formula phi, then if sigma entails phi, then the substitution of sigma entails the substitution of phi. Now then, finally, a logic is going to be understood as a pair where we have a formula algebra Fm and a turnstile consequence relation, turnstile S, and the logical language L and the set of variables are going to be given. This turnstile S, this consequence relation, will be a substitution invariant consequence relation. Now, this logic will be called finitary if it satisfies the compactness property. This is given in C5. Now, the other part of the set of preliminaries is the concept of a logical matrix. So a logical matrix for a language L or an L matrix is a pair A, comma F, where this boldface A is an algebra of type L with universe regular face A. The second component of the pair AF is a subset of the universe. It's the set of designated values. It's also called a filter. The algebra A can also be called an algebraic reduct of the matrix. A trivial matrix is one with a one-element universe. And we will denote a trivial matrix of type L by boldface 1 sub L. Its universe will be denoted by the singleton omega. So omega would be the singleton element of the one-element universe of a trivial algebra. The subscript L will denote the logical language in play. And then the trivial L matrix will be the matrix 1L, comma omega L. So the only element is designated there. Now, given L and V, an L matrix and an L matrix AF, each formula phi of the universe of the formula algebra has a unique interpretation in the algebra A, depending on the values in A that are assigned to its variables. Now, algebraically, this just means that there is a homomorphism from the formula algebra to the algebra A, and V of phi is the interpretation of the formula phi in the algebra A under this function B. Such a function, such a homomorphism is called an assignment or valuation. And given a logic S, that is FM, comma, turnstile, sorry, was there a question? Okay.
I don't think so. I don't think so.
Okay. Given a logic S in a language L, an L matrix AF is called a model of S if for every valuation, that is, if for every homomorphism from FM to A and every sigma set of formulas, phi a formula, if the elements of sigma are designated, that is, they are members of F, and sigma entails phi, then phi is also designated, sent to the set of designated values by the homomorphism V. Now, the class of all matrix models of S is denoted by this mod S, and then we go on into this this class of L matrices with respect to which, so the logic L is said to be complete relative to a class of L matrices if the following conditions are satisfied. First of all, the class M is contained inside the set of all models of S. And the second property is satisfied, which says that if sigma does not entail phi, then there is a matrix in the given class of matrices M and evaluation V from FM to A such that the elements of sigma are designated, but phi is not. So in a way, there is a member in M which provides the justification for which sort of which justifies that sigma does not entail phi. Such class of matrix models M is called a matrix semantics for this logic S. Now, logics may be defined using logical matrices as well. So if you have a class of L matrices M, we can define a logic S sub M where FM is still the formula algebra of type L over a set of variables V, and turnstile M is defined in the following way: sigma turnstile sub M phi, if and only if for every matrix in M and for all valuations V, this property is satisfied that V sigma is a subset of F implies that V of phi is a member of F. Now, a logic S in the language L is complete relative to a class of L matrices M when the turnstile is the same as the turnstile that is induced by the class of L matrices M. That is, the logic that is defined using the class of matrices is the same as the logic S. Okay, now we come to an example. So this is the paraconsistent weak Kleene logic. Here, the logical language consists of 5 elements. 2 of them are of arity 2. So this is the conjunction, disjunction, negation. 0 and 1 are constants or operators of arity 0. WK is the L algebra given by these tables. Now, the boldface FM is as before the formula algebra of type L over a countable set of variables V. Now, PWK, that is paraconsistent weak Kleene logic, can be described as the logic FM turnstile PWK. So this logic is induced by the given matrix. The matrix is WK, the algebra is WK. The set of designated elements is 1 and omega. Okay, so before I go into the next slide, there's something to notice here, that this omega is functioning as an absorbing element. So anytime omega is composed with any other truth value, the result is omega. And if you delete the row, the omega row and the omega column, all you have is Boolean. So 0 and 0 is 0, 0 and 1 is 1, 1, and so it behaves, and conjunction, disjunction, negation, they behave classically, just as in classical logic. So with that thought, we go into the next slide, which is a bit of a digression into infectious logics. So PWK is a member of a broader family of what are called infectious logics. So what is an infectious logic? An infectious logic is exactly what we saw here, where omega is an absorbing element. So in an infectious logic, there will be an absorbent or infectious or contaminating truth value. That is a truth value. Whenever it's assigned to a formula, every formula that contains it as a subformula will also get that same infectious value. Now, the logic that is induced by this same algebra with only 1 as the designated element is also an infectious logic, and it's known as Bockfar's logic of nonsense. It is also easy to check that if the infectious truth value is not designated, then we will get, there is an infectious value, but that is not designated, then we'll get a paracomplete logic, which means the OR introduction rule of classical logic will fail. And if the infectious truth value is taken as a designated truth value, the logic will be paraconsistent. We'll come to paraconsistency later on. An example of a paraconsistent logic is PWK. We will come to a broader discussion of paraconsistency later in this talk. Now, there are some ways of interpreting this infectious truth value. Some of these are as follows. So it can be understood as nonsense. So a statement gets this infectious truth value means that it's to be treated as nonsense. So this was Bockfar and Halden's interpretation. So The infectious truth value is assigned to those sentences that are neither true nor false, and hence are truth value gaps. Then there was Fitting's epistemic interpretation. So suppose there is some experts are trying to decide on a certain thing, on a certain topic, and the presence of opinions, both or neither, for and against on some statement. So let's say we are trying to decide a yes or no question on a particular topic, and there is an equal number of for and against, or neither. So there could be neither. So there are two ways of interpreting, depending on whether your infectious truth value is designated or not. Then there is computational failure. This was by Thomas Ferguson. A computer may fail to retrieve the value of a given sentence, that is the truth value of a given sentence. Now that should be taken as different from the computer retrieving the value, the truth value, and the truth value is false. So there is a difference between false that is retrieved by the computer and the failure of the computer, computational failure. And the last one that I'm going to talk about is off topic. This was by J.C. Beale. The infectious value is assigned to sentences which are off topic. So for example, if you say that 5 is blue, or 2 + 2 is equal to 4, that particular sentence is off topic because part of it is off topic. You're not supposed to talk about colors when you're talking about numbers. All right, now I'll shift a little bit. So anyway, the infectious logics was a bit of a digression. I'll come to some algebra here. So this particular definition was due to Płonka, and it was given in 1967. So this is a directed system of algebras. It consists of a joint semilattice, a family of algebras of the same type with disjoint universes, and a collection of homomorphisms f sub ij going from the algebra a sub I to a sub j whenever I is less or equal to j. And these set of homomorphisms will satisfy the following two conditions. That is, if fii is the identity homomorphism for each I, and whenever you have I less equal to j less equal to k, then f of f sub ik is the composition of f sub jk and f sub ij. So that things fall into place nicely. And then finally, we have the Płonka sums of algebras. This was up to the second point. This was already there in Płonka's paper in 1967. The last condition was added in 1984. So let's see what this is about. So first of all, we have a directed system of algebras. The Płonka sum of x, this is denoted as P sub L of x, is the algebra whose universe will be the union of all the universes. Now for every basic operation, so this Płonka sum will also be an algebra of the same type. Now we have to find the basic operations of this big algebra that we are getting. So for every basic operation f of positive arity, if you have a1 through an in the universe of this PLX, then the operation will be defined as follows: F superscript PLX of a1 through an. First of all, you will export all the J denotes the upper bound. So this is why we need an upper semilattice. So there will be an upper bound of I1 through IN. First of all, you export all the A1 through AN to this A sub J, where J is the upper bound of I1 through IN, and then you compose those in A sub J. So in case you have nullity operations or constants in the algebras, then you need the indexing semilattice I to have a bottom element. And then what you do is that the nullity operation in the Płonka sum will be the same as in the algebra that is indexed by this bottom element. So this is the description of a Płonka sum. The idea is to have a way of gluing together algebras of the same type into a big algebra, and at the same time ensuring that some of the properties of the base algebras are transferred to this bigger algebra that you have, which is what we are calling the Płonka sum. All right, now this definition of a Płonka sum of algebras of the same type was extended recently in a paper in 2021. This is the directed systems of, first of all, they defined the directed system of matrices. It's defined similarly. First of all, you have a joint semilattice. The only difference is that you're now dealing with matrices, so you also have to deal with the filters f sub I. And in the homomorphism clause, you have to have this clause that the homomorphisms are not only going to satisfy the conditions here in the that we had earlier, but we have to make sure that when you do Fij and of capital F sub I, that is the filter of the ith algebra, then you land inside the filter of the jth algebra. So the filters have to be sort of compatible that way. All right, now then they defined this Płonka sum of matrices. So suppose, first of all, X is a directed system of matrices. The Płonka sum is then defined as you would expect. You would do the Płonka sum of the algebras, and you will take the filter will be the union of the filters of all these algebras. Now, given a class M of matrices, PLM denotes the class of Płonka sums of directed systems of matrices in M. Now, we'll deal with a special case. A, suppose, is an algebra of some type L, and one is the trivial algebra of the same type. Then the two-element family A, comma 1, if you take the identity homomorphism, it becomes a directed system of algebras. Now, the Płonka sum of this directed system will denote by O plus 1, and O plus 1 is the L algebra with universe A union omega. Remember that one has only one element, which we are denoting by omega. And then we have for any NRE basic operation F of A plus 1, A1 through AN will be equal to F of A1 through AN in A if all of these A1 through AN are in A. Now, if any of these A1 through AN is omega, then of course you get omega, because all you had in your set of homomorphisms were the identity endomorphisms and the unique homomorphism A to 1. Now, A to 1 will send all the elements of A to omega. So if any of these elements is omega, you are supposed to export all the elements under consideration. That is, all of these A1 through AN to the algebra 1, that is the trivial algebra. That means everything gets converted to omega, and then compose them. If you compose them in 1, of course, you will get only omega. So this is an algebraic way of looking at absorption. The absorbing element or the contaminating element that we saw earlier when we were discussing PWK, this is the algebraic way of seeing absorption. Okay. Now, this can be lifted to matrices as well. So if you take a two-element family, AF, and this trivial matrix, I mean, these are all L matrices. L is fixed over here. Then the Płonka sum of this distributed, the directed system of matrices is the L matrix AO plus 1 and F union omega. So you are just adding omega to the filter of F. Thus, we are beginning to see what or how we can interpret the matrix WK1 omega that we saw before. We'll come to that in a moment. Now then, the class of Płonka sums of Boolean algebras is a model for PWK. This was proved in 2017. And as I was saying, in particular, WK1 omega is B2 O plus 1 omega, where B2 is the two-element Boolean algebra. So if you recall, when we had the matrices shown, the WK algebra shown, I pointed out that if you delete the omega rows and omega columns, then what is left is essentially Boolean, the Boolean algebra columns and rows. So that this is an explanation of WK algebraically. Now then we come to a further characterization of PWK. We have already seen PWK defined as using the matrix WK1 omega. This is highlighted here as well. So this is the logic induced by the matrix WK1 omega. By CPC, we will denote, we will mean classical propositional logic. And then we introduce one further notation, one further piece of notation for any formula phi. Var phi is the set of variables occurring in phi, and this is extended to var gamma, where gamma is a set of formulas. This is just the collection of all variables occurring in any formula in gamma. Now, we come to this theorem, which was given in 2014, that if gamma gamma entails phi in PWK, then there is a gamma prime subset of gamma such that var gamma prime is a subset of var phi, and gamma prime entails phi in CPC, and vice versa. Okay, so since CPC is finitary, we can have such a gamma prime that is finite. So in other words, this gives us a characterization of PWK, because whenever we can say that gamma entails phi in PWK whenever there is a finite gamma prime which entails phi in CPC. Now this is generalized in this definition here of a left variable inclusion companion of a logic. So suppose you have a logic, FM turnstile. The left variable inclusion companion of this logic is this logic S sub L, where the turnstile L is defined as follows, just like in this characterization theorem for PWK, gamma turnstile sub L phi, if and only if there is a gamma prime subset of gamma such that variable gamma prime is a subset of variable phi and gamma prime entails phi. In other words, there is a gamma prime subset of gamma which entails phi in the original logic, and the variables in gamma prime are contained inside the variables in phi. This is left variable inclusion. Now, there is also a right variable inclusion, which is sort of similar, and you can probably guess what this is. I'm not going to talk about right variable inclusion in this talk, but right variable inclusion is defined in a similar way. So given a logic, you can have a right variable inclusion companion where the turnstile R is defined as follows: gamma turnstile sub R phi, if and only if gamma entails phi and variable phi is contained inside variable gamma, and or sigma is a subset of gamma, and sigma is a set of inconsistency terms for S. So I'll leave it over there because I'm not going to talk about right variable inclusion companions here. These are the left variable inclusion companions, and right variable inclusion companions of logics are also sometimes called containment logics. Falls under a broader category. Now, logics of left variable inclusion, some examples. So first of all, PWK is a left variable inclusion companion of CPC. That is because of that 2014 theorem by Kleene and Carrara. And we recently saw that intuitionistic, if we replace CPC by intuitionistic propositional logic, we get a similar result. So we got this logic, intuitionistic paraconsistent weak Kleene logic is the left variable inclusion companion of intuitionistic propositional logic. Bok-First logic, on the other hand, is the right variable inclusion companion of CPC. This can be checked, has been checked, but I'm not going into that here in details. Now, some general properties. These are easy to check, actually. So if you have a logic and your original logic is S, and this left variable inclusion companion is S sub L, then a formula phi is a theorem of the original logic if and only if it is a theorem of its left variable inclusion companion. And then another one, if you have a logic S and its left variable inclusion companion is S sub L, then for any set of formula sigma and any formula phi, if there is no variable in common between phi and sigma, and phi is not a theorem, then you cannot expect to have sigma entail phi in the left variable inclusion companion. This is also easily derivable from the definition of left variable inclusion companions. Okay. Now, some very recent theorems from 2021. So if you have a logic S and X is a directed system of models of S, then the Płonka sum of this directed system of models of S is a model for the left variable inclusion companion of S. And the second theorem is even more surprising, that if you have a logic S and M is a class of matrices of the same type as Fm containing the trivial matrix of type L, if S is complete relative to M, then SL is complete relative to PLM. PLM is the class of Płonka sums of the directed systems of matrices in M. Okay, so again, coming back to PWK, suppose M is a class of Boolean matrices containing the trivial Boolean matrix. Then PWK is complete relative to PLM. Okay. Now, the case of IPWK, so here, when we are describing IPWK, we take the language L to contain conjunction, disjunction, implication, negation, 0 and 1. V, FM, boldface FM, regular face FM are as before. Now, any hiding algebra can be seen as an algebra of this type L. You consider the class of all hiding algebras, hiding matrices, let's say, a hiding algebra, and 1 is this set of designated, the singleton 1 is the filter. IPC is complete with respect to H. This is well known. The trivial L matrix is a member of this script H. Then if you take the left variable inclusion companion of IPC, this is going to be sound and complete relative to the class of Płonka sums of the directed systems of matrices in PLH. This is by the previous theorem. Then in particular, for each hiding algebra H, the Płonka sum of the matrices H1 and the trivial matrix, we'll denote this, let's say, by H sharp 1 omega. Now, the intuitionistic paraconsistent weak Kleene logic is the logic defined using the class of L matrices H script H sharp, which just contains all the sharp matrices. Thus, we can conclude that IPWK is equal to IPCL, the left variable inclusion companion of IPC. So we have this theorem. So for all sigma and alpha, sigma entails alpha in IPWK if and only if there is a delta subset of sigma such that variables of delta are contained in variables in alpha, and delta entails alpha in IPC. So this is very similar to the theorem that we got for PWK in terms of CPC, except CPC has been replaced by IPC. IPC is finitary, so such a finite delta can be found. So this is the corresponding theorem for intuitionistic case of the earlier theorem for classical propositional logic and PWK. Now we come to the restricted rules companion. So this is really the area where our contribution lies. Of course, we did the IPWK, but those were proofs which are similar to the ones for PWK. But now the question that arises can be described as follows. So first of all, we talk about this. Our motivation for this work, a Hilbert-style presentation of PWK, which is the left variable inclusion companion of CPC, as we have mentioned before, consists of the same set of axioms as CPC and has a rule of inference, which is a restricted version of the modus ponens rule. This Hilbert-style presentation of PWK was given in 2017. Similar to that, we obtained a Hilbert-style presentation of IPWK. This consists of the same set of axioms as IPC and the same restricted modus ponens that we have given over here. The restricted modus ponens is just that alpha beta follows from alpha and alpha arrow beta only if variables in alpha are contained in variables in beta. Now, the question from these two cases that arises is the following. Is it always the case that a Hilbert-style presentation of a logic of left variable inclusion can be obtained from that of the original logic by just restricting the rules of inference? So in both PWK and IPWK, we saw that the axioms are not changed. We are only changing the rule of inference. We are putting in a variable inclusion clause in the rule of inference. So is it always the case? So thus we define this companion of any logic. So first of all, we call any logic induced syntactically via a Hilbert-style presentation, a Hilbert-style logic. So we are keeping the the presentation fixed, the Hilbert-style presentation fixed. Then the logic that is induced by the Hilbert-style, that Hilbert-style presentation is a Hilbert-style logic. Now suppose S is a Hilbert-style logic with a set of axioms A, and R sub S is a set of rules of inference. We define the restricted rules companion of S as the Hilbert-style logic with the same set of axioms, and the set of rules of inference is where we are putting in a variable inclusion clause for each of the rules of inference of the original logic. So gamma, alpha is derived from gamma. If this is a rule of inference in the original logic, then the corresponding rule in this restricted rules companion will be the one, those instances where variables in gamma are contained in the variables in alpha. So some instances of these rules of inference are taken and others are rejected. In other words, you can see this as the, you can apply a rule only when, let's say you can go from gamma to alpha only when variables in gamma are contained in variables in alpha. Just like in the restricted modus ponens case, you can entail beta from alpha and alpha arrow beta only when variables in alpha are contained in variables in beta. Now, examples of these, PWK is, or the left variable inclusion companion of CPC is the restricted rules companion of CPC as well, because of the result by in 2017 that I just mentioned here, the 2017 result. Then IPWK is also the restricted rules companion of IPC. And this is what we showed in our paper. And as I mentioned, the proof is very similar. Now, so we started investigating these restricted rules companions in more detail. The first thing we noticed is that just like the left variable inclusion companions, the restricted rules companions also share the same theorems with the original logic. There is no loss of theorems. Second, this was an interesting result that the restricted, whenever you get something, whenever you have an entailment in the restricted rules companion of a logic, you also have it in the left variable inclusion companion of the logic. So in other words, turnstile RE is a subset of turnstile L. But the interesting part was that the reverse inclusion does not hold. So our question gets answered in the negative. An example will do the proof. So here we took a toy example of a logic where there are no axioms, only two rules, R1 and R2. One is the conjunction elimination, the other one is the disjunction introduction. And we took the restricted rules companion of this logic, this toy logic, and we see that for the R1 needs to be restricted because we need to put a variable restriction. This beta is forgotten in the conclusion, so we need a variable restriction. In R2, we do not need any restriction because everything in alpha is also there in the conclusion. Then we took a derivation. So suppose P and Q are two distinct variables. And we consider the following derivation in S. So from P and Q, we get P by applying R1. And then by applying R2, we get P or Q. So from P and Q, we can derive P or Q in the original logic. Now, since the variables in P and Q are the same as the variables in P or Q, this entailment also holds in the left variable inclusion companion. However, this middle step wherein we derive P from P and Q cannot be done in the left variable inclusion companion. But if you notice that we cannot do this in the restricted rules companion, since this application of R1 in step 2 cannot be replaced by an application of the restricted version of R1. So thus, in this case, we have that turnstile RE is a proper subset of turnstile L, and hence you cannot have SL equals SRE. Okay, so then we started thinking about justifications for this divergence. Now, what could be a possible justification? We see that the restricted rules companion of a logic enforces a variable inclusion restriction locally at each step of a derivation where a rule is being applied. a rule of inference, whenever it is applied at a step of a derivation, you have immediately a variable inclusion restriction put in there. On the other hand, the left variable inclusion companion of a logic, it outsources the steps of a derivation to the original logic with the unrestricted rules of inference. So if there is a rule which allows you to forget a variable and another rule which allows you to introduce a variable, you can negate each other. And therefore, your overall entailment could still have the global variable inclusion restriction, but it could be that at each step, you are not following the variable inclusions. So therefore, there is this falling apart of the two companions of a logic. Now, the last part of this discussion about restricted rules companions is where we start thinking about some necessary sufficient conditions wherein these two companions will converge. So the answer, at least a partial answer, comes from this innocent looking theorem from classical and intuitionistic logic, namely the deduction theorem. So we all know that the deduction theorem tells us that if you have beta following from sigma union alpha, then sigma entails alpha arrow beta and vice versa, the converse of the deduction theorem. So we start investigating with this deduction theorem. It turns out that if the original logic has the deduction theorem, the left variable inclusion companion of it will also have the deduction theorem. But the same is not true about the converse. If the original logic has the converse of the deduction theorem, a restricted version of that converse holds in the left variable inclusion companion. What is the restriction? This restricted version says that your variables in alpha must be contained inside the variables in beta. If you want to export alpha from the right-hand side of the turnstile to the left-hand side. Now, we found a sufficient condition for the two companions to converge using this deduction theorem. So suppose you have a finitary Hilbert-style logic such that modus ponens is one of the rules of inference in this logic. Now, suppose further that the deduction theorem holds in S, then the restricted rules companion of S coincides with the left variable inclusion companion of S. So there's two things. The original logic is a finitary Hilbert-style logic with modus ponens as a rule of inference, and the deduction theorem holds in S. Then the restricted rules companion and the left variable inclusion companion of this logic are going to be the same. So thus, the fact that PWK is equal to the left variable inclusion companion of CPC and also the restricted rules companion of CPC, and similarly IPWK is the left variable inclusion companion of IPC and also the restricted rules companion of IPC, these are now just corollaries of this theorem that we proved in this paper. The question of a necessary condition, though, could not be answered. It needs some more work, but we are thinking about it. Lastly, I will stop with some discussion about paraconsistency of these systems, these restricted systems. Now, first of all, a paraconsistent logic is a logic where a negation inconsistency, that is the presence of a contradiction, does not lead to triviality. Now, classical logic, intuitionistic, propositional logic, they are not paraconsistent because of this principle of explosion, which says that whenever you have contradictory statements, everything follows from the contradiction. It is well known that paraconsistency is usually defined as the failure of this principle of explosion. So logic is paraconsistent if and only if the principle of explosion fails in it. Now, there is also another law, which is another principle that is linked with paraconsistency. This is called the law of non-contradiction, which says a syntactic version of this can be put as that for any formula alpha and not alpha, not of alpha and not alpha is a theorem. And CPC and IPC both validate ECQ as well as this law of non-contradiction. However, there are logics where one holds while the other doesn't. So, for example, PWK is a logic where explosion fails, ECQ fails. You can see that ECQ fails by saying that by taking alpha to be something which gets omega, gets the truth value omega, and beta as something which takes the truth value 0. In other words, you can have a variable p. P is mapped to the truth value of p is omega, and on the other side of the turnstile you have q, which is a different variable than p, and it takes the value 0. So explosion fails. However, the law of contradiction holds in PWK. And then there is the Lukasiewicz three-valued logic where the law of non-contradiction fails, but ECQ holds, explosion holds. So ECQ and LNC are independent of each other, and failure of LNC alone cannot prevent explosion and hence cannot guarantee paraconsistency. Paraconsistent logics where both ECQ and LNC fail are therefore sometimes called strong paraconsistent logics. Now, what has that got to do with our situation here? Well, one thing is, suppose L is a logical language which has negation in it, and then if you have if you take a logic on this logical language, and there exists an alpha that is not a theorem, and there is a variable which is not a variable in alpha, then ECQ fails in the left variable inclusion companion. Okay, so not everything is a theorem, and there is a variable outside. So there is an adequate supply of variables, and there is at least one non-theorem. Then we can see that the left variable inclusion companion of this logic will be paraconsistent. Now, suppose this logic is if you take a Hilbert-style logic with the same conditions, and then we can see that ECQ fails in this restricted rules companion of this logic as well. It has to, because the restricted rules companion is contained inside the left variable inclusion companion.
Shankho,
yes.
Can you please make it a little short?
Yes, I am almost done. Just give me just a minute. So suppose you have S where LNC fails, then SL is strongly paraconsistent because theorems would carry over from the original logic to the left variable inclusion companion, and they will also carry over to the restricted rules companion. Thus, we have this summary. So if you have a non-paraconsistent logic where LNC holds, you are guaranteed to get at least a weakly paraconsistent logic, which is where just ECQ fails. LNC will still hold because theorems carry over to these companions. If you have something which is not paraconsistent, but LNC fails, like three-valued Lukasiewicz logic, then you will have the left variable inclusion companion and the restricted rules companions, which are strongly paraconsistent. If you start with a weakly paraconsistent logic, you get a weakly paraconsistent logic. If you start with strongly paraconsistent logic, nothing changes, everything stays the same. So thus we have this summary. So you have some non-paraconsistent logics which can whose companions are going to be paraconsistent. Okay, so that was it. Thank you.
Thank you, Shanko, for an enriching and a well-lit presentation on mathematical logic. Now it's a time to get some feedback from the audience. Any query, any comment?
Yes, Shanko, thank you for that nice talk. I mean, I was a little familiar with this, but not with all the details. Now, I just wanted a clarification about this one of the last few results you were quoting. There you had this assumption of finitary Hilbert system, I think, right? So if you can just show your slide. So what was that about?
Yeah, so where exactly?
Yeah, I think some 2-3 slides ago. Just before you began the paraconsistency. Yes, here.
Yeah.
So what was this assumption about? Was not.
So the assumption of finitary, so your original logic is a finitary Hilbert style logic. Modus ponens is the rule of inference, and the deduction theorem holds in S. Then the restricted rules companion will coincide with the left variable inclusion companion. That is the result.
Right. So what is the finitariness's role here? That's what I was.
I think the finitariness is coming from is required in one of the verifications. Somewhere in the theorem, you need a finitary assumption in the proof.
I see. Okay. So. Right. Okay, anyway, that was just a clarification I wanted.
I think finiteness was required while going back, because you have to go back and forth.
Yes, exactly. So you have to apply the converse of the, or you have to apply modus ponens to.
Yeah.
Okay, I see. Okay, thanks.
Any other comment or query? I think everybody is satisfied with the talk. So thank you, Shanko, again for the nice talk. And now over to Shorab or Purvita, whoever is available.
Okay, thank you so much, Shankoda, for such a nice talk, and thanks, Monipadi, for chairing all the sessions for today. So now I would like to request Professor Ranjan Mukhopadhyay to conclude the formal part of the 21st CLC Annual Meet 2022.
Okay.
So over to you, Ranjan.
Can you see me?
Yeah, we can.
Okay, and you can also hear me because you're responding.
Yeah.
Okay, so Purvita asked me to, requested me to conclude the annual meet of 2022. That can be done in a minute, not even in a minute, it can be done in a second. I conclude it. Okay, that concludes it. So it's fine, but then I will have to give some comments on behalf of everybody, because we have assembled here on virtual mode during this pandemic time, and are holding this annual meet. And then it has been a success that definitely all of us are feeling, because we have had very prominent keynote speakers like Ramanujam himself, then Alessandra, then Benedict, then Michael Rashin, and then also Amitadi. All of them are very busy. That could be seen, or I mean, very much engaged. That could be seen from the talks that they presented. But then even then they found out time to share with us with the thoughts that they really delivered here. So that is the benefit that we have had during this pandemic time, and we have been having this benefit in all the annual meets that we are having, and also we had other contributed talks from many, like Shankhu right now, then Ryan was there, then Vinita was there, then Prosenjit was there. I do not know whether I'm missing anybody else, but then please forgive me if I'm missing. But then Moshur, yes, Moshur was there also.
Romit as well, I guess.
And Romit was there.
Romit was there, yes. That's, but Romit is very young, I could see. Okay, so we all have really enjoyed these 4 days, and I wish that we could have some such occasions more. And the thing is, one thing I think has been very good is that we didn't have to travel to some particular place to meet and discuss these things. We could do all these things from our homes, thanks to the internet, etc., and all the troubles that Purvita and Shourav took, or maybe some others helping them to manage all these technicalities. But that has really helped us a lot. So I wish everybody well, and that they prosper more, and then come back again next year, the next occasion for annual meet, to enrich us with such more talks. Thank you so much. Okay, so then it's now transition for Adda, I think. You said, Purvita said there will be Adda session.
Yeah, we were thinking about that. And
but then I think everybody is very, very tired.
Yeah, that's everyone's decision now.
Okay.
It will be a very good ending if Mohua or Shoma ends it with a song.
Ah, yes.
That's good.
Shoma, sing some Polish song. Shoma is there?
Where is Shomadi? Yeah, Shomadi is there.
I don't think that Polish song will help to.
Why?
Because you will not understand anything.
No. That is the best thing. Without understanding.
No, that's not.
That is left variable inclusion, that will be. We will generalize on that. Don't worry.
Are you really that much fond of Polish songs?
Yes. You sang for us someday. You remember?
Yeah, that I know, but I without understanding meaning, whether it would be at all good to listen some.
Okay, you will tell us the meaning as well. First sing it.
No, Polish song is not good to sing.
Okay, then will it be a Bengali one?
No, I think Mohadi can sing. I am not singing for
quite some time.
Mohadi is there. Mohadi can sing something.
Hey,
Mohadi can do, and then I can try to find out something, maybe Bengali, not Polish. Yes, you are, to me.
রাত দুপুরে সেই বিশ্বলোচনের দুপুরের জায়গায় রাত্রি হয়ে গেল।
তো তাই জন্যে
না ঠিকই আছে, গ্রীষ্মের বদলে শীত, দুপুরের বদলে রাত, ঠিকই আছে, সবই চেঞ্জ হচ্ছে।
এবার শেষ করা ভালো। এই সময় একটা গান দিয়ে দে।
I don't know. Nothing is quickly coming to my mind, and maybe something is coming, and maybe I am afraid Mohadi can say later that like I remember. I think everyone here is Bengali, so I can speak in Bengali.
প্রত্যেকে বাঙালি কোথায় আছে?
No, no.
No, আমি দেখলাম রামানুজম ছিল, that's
বাঙালি
why.
আছে, অবাঙালি আছে তো।
No, আছে?
গায়ত্রী দেখতে পাচ্ছি।
Anyway, so I was
Doesn't matter.
remembered about Mohadi because I remember once in Isla in Delhi I started singing something, and Purvita, do you remember the song?
ও একদম আমার এই দেহখানি তুলে ধরো।
আমি যেই গাইতে শুরু করেছি আমার এই দেহখানি তুলে ধরো,
তোমার তো দুপুর, তোমার তো দুপুর, আমাদের তো রাত, গভীর রাত।
না, আমার দুপুর নয়, আমার এখন 4:40।
বিকেল।
I just want to add one thing, that probably we are missing that Abhishek Shankaran is also here.
Oh yes, Abhishek S is there.
Abhishek is here?
Yes.
I ভাবলাম সৌরভ বুঝি গান গাইতে চাইছে।
তুমি কি তাড়াতাড়ি শেষ করতে চাইছো মিটিংটা?
তোর ঘটম কোথায়? তোর ঘটম নেই সঙ্গে?
ঘটম এখন হবে না। গান এখন গান।
আমার যে গান মনে পড়ছে সেই গানে মৌহাদির আবার ওই রকম রিঅ্যাকশন হবে কিনা আমি জানি না।
কি করেছিলাম, কি রিঅ্যাকশন হয়েছিল আমার মনে নেই, হেসেছিলাম।
আমার মনে পড়ছে তোমারও অসীমে।
গাও না, সুন্দর গান।
ওকে, দাঁড়াও লিরিক্সটা খুলি।
তোমার লাস্ট গান শুনেছিলাম এমন মানব জনম আর কি হবে।
হ্যাঁ, আর ওই দুটো। আচ্ছা, আমি অন্য একটা গাইতে পারি, সেটা অবশ্য সেটাও আর কি ওই ধরনেরই। ওই সিরিয়ালটা আমার খুব পছন্দ, গানগুলো ছিল প্রথমা কাদম্বিনী। জানো গানটা আরেকটা? আমার হাত বান্ধবী।
করো।
আচ্ছা, ওইটা গাইতে পারি বেশ। দাঁড়াও তাহলে একটু জাস্ট সার্চ করে নি। পেয়েছি, চেষ্টা করছি। আমি অনেকদিন এই গানটা গাইনি। আমার হাত বান্ধিবি পা, মেবি আমি একটু নিচ থেকে শুরু করি। আমার হাত বান্ধিবি পা বান্ধিবি মন বান্ধিবি কেমনে, আমার চোখ বান্ধিবি মুখ বান্ধিবি পরাণ বান্ধিবি কেমনে, আমার হাত বান্ধিবি পা বান্ধিবি মন বান্ধিবি কেমনে, আমার চোখ বান্ধিবি মুখ বান্ধিবি পরাণ বান্ধিবি কেমনে, আমি না গেলাম যমুনার ঘাটে না তুলিলাম জল, না হেরিলাম তারে সখী না হইলাম চঞ্চল, আমি না গেলাম যমুনার ঘাটে না তুলিলাম জল, না হেরিলাম তারে সখী না হইলাম চঞ্চল, আমার ইচ্ছা বান্ধিবি সোহাগ বান্ধিবি অনুরাগ বান্ধিবি কেমনে, আমার হাত বান্ধিবি পা বান্ধিবি মন বান্ধিবি কেমনে, আমার চোখ বান্ধিবি মুখ বান্ধিবি পরাণ বান্ধিবি কেমনে।